Indeed. All right. So let's get started. Um, so far in this class, basically everything we've done up through project one and the first couple of homeworks and everything and all we've been covering in lecture so far, with the exception of our little warm up at the beginning, has just been using a single processor core. But today we're going to start to talk about programming multiple cores to get even more performance. If you remember back to the first lecture and to the, in particular, the matrix multiply case study that was added on after the first lecture, we saw that that was a really key factor for getting peak performance out of modern machines. You can easily get a factor of dozens potentially on the sort of chips that we're programming on AWS. And multi-core programming like this is also going to be the focus of the second project, which comes out later this week. So just as soon as the first project wraps up, we switch over to a multi-core programming project where you're doing another, going to be building a screensaver, I think, building another kind of graphics-like application and start using multi-core parallels and using some of the ideas that we're going to talk about today and then dive into more detail on over the next few lectures. All right, sorry, let's focus. All right, so, performance engineering with one core, which is, again, what we've done so far, is arguably hard enough. So why do we have to make it even harder by worrying about programming a whole bunch of cores at once? Well, basically every modern processor that you'll work with looks something like this, like we have on the slide here. This is an Intel processor from a few years ago, from roughly the same generation as the AWS machines that we use in 6172 still. But from big servers to your laptop to your cell phone, even my watch today has multiple cores in it. And a modern processor chip generally combines, like you can see in the floor plan diagram of this Haswell E processor, combines many independent cores. In this case, we can see 8 of them here. With potentially some shared cache memory. That's what you see in the middle in this case. And usually a whole bunch of other logic, accelerators for different kinds of specialized computation, I/O to talk to memory or USB or the network or other things. All packaged up into one big chip. But why is it that instead of doing all of our computation kind of as one serial program on one really big processor core, why is it that these days, basically every processor you're going to interact with has a bunch of different cores? So harkening back to lecture 1, does anyone remember why we wound up with a whole bunch of processor cores today? If you want to post reasons why this might be in the Slack. Good question. Before we get to that, what's the uncore? Uncore is Intel jargon for, like I was saying, all that stuff, like all the specialized logic, like potentially GPU logic, potentially the on-chip network to connect all the different components, potentially things like USB or Ethernet or PCI controllers, reflecting kind of the cultural centrism of Intel architects, where the core is the fun, important thing, and everything else is second class. They call that other stuff uncore, meaning the stuff that's not the main processor core. But it's basically everything else in the system on chip that's not just our main processor cores or big main caches. And again, that's mostly Intel jargon for sort of a catch-all for all that stuff. But does anybody have any ideas or any memory of why it is that why modern processors have a bunch of cores instead of one really big core? A few people typing. Something about distance. That's actually a very deep answer. It's not quite how we explained it, but I think that's actually related to something very fundamental about it. Yeah, processor clock speed mostly stopped growing. Physical constraints, like heat, and how many operations can easily be parallelized. This is great. This is all getting at different facets of the core issue. And basically, I think about it in terms of kind of 3 factors. So on the one hand, Moore's law has continued. It's been going on since, I guess, the late 60s with the first integrated circuits. And Moore's law, which is that every 18 to 24 months, the number of transistors we can build in a given area of silicon, like the size of those transistors, well, the number we can build in a given area doubles, the size of them falls by half. And so the amount of logic we can build on a chip of the same size or for roughly the same cost keeps doubling. So every 2 years, we're following this exponential doubling curve. So our designs can get more and more complicated, but a while back, specifically about 15 years ago, our ability to continue scaling voltage and clock frequency effectively hit a wall. So for the first couple decades of Moore's law, as those transistors became smaller, the physics in that regime was also such that you could switch them about twice as fast, which meant that the clock speed could double at about the same time. But in more recent history, starting in about 2005, we hit a regime where the transistors were small enough that the dominant effects, that was basically no longer the case. And the amount of energy, the amount of power you needed to drive transistors if you wanted to keep increasing their clock frequency started getting out of control really fast. At the same time, and this is something that's not talked about that much, but at the same time, it happened that the processor cores we were building at about that point were starting to hit diminishing returns in terms of their ability to invest extra transistors in exploiting instruction level parallelism. So investing extra transistors in building one core that could run multiple instructions at the same time at larger and larger scales. So how could we use twice as much logic to do twice as much work, on only one stream of instructions or one thread? Some basic architectural optimizations that we talked about a few lectures ago do a pretty good job of that. So, a little bit of superscalar execution, out of order execution, speculation, throwing some logic at building branch predictors. That works great at the beginning, but if you want, past some level of complexity, you get sublinear payoff. If you make your branch predictor twice as big, you don't wind up running your processor twice as fast. If you make your superscalar window, the number of instructions that you can execute in parallel twice as large, you don't generally get actually double the performance. So all of that wound up hitting at the same time, all of the kind of changes in regime of computer architecture and device physics around the early 2000s, and in particular around 2004 or 2005. And so as a result, we wound up with the computer architecture community basically taking a hard left turn in processor architecture around 2004 or 2005. So this graph shows data points for the transistor count, so basically the complexity or the amount of logic that we have, the clock speed in megahertz, and the number of independent processor cores for hundreds of commercial processor chips from the 1970s up to 2015. So the y-axis here is a log scale, so linear progress, like you roughly see in transistor count, means exponential growth over time. So growing from 1 to 10 to 100x as much, all the way up to, these days we're over 1 million times as much logic on a chip as we had in the early 1970s. So as you can see, the number of transistors that we could build kept growing. That was the Moore's law trend. That's kept up reasonably well, although in the last few years, starting at about 2015, 2016, it started slowing down significantly. And there's reason to believe that we're in kind of the technology roadmap we've been on since the late 1960s, we're nearing the end of the ability to continue this scaling. So it's gotten a little bit slower in the last few years, and it's likely to kind of asymptotically slow down over the next decade. And we'll only get probably a few more doublings building things the same way we know how we've been doing for a long time. But a similar cliff happened back in 2004, 2005 with clock speed. So you can see clock speed was growing on a nice exponential curve also. got about 1,000 times faster over that period, getting up into the gigahertz regime, but then it basically stopped increasing. And in fact, many designs started running at lower clock speeds for energy efficiency reasons. But at that same time, you can see, well, for 35 years, basically every microprocessor chip had a single processor core on it. Starting just before 2005, all of a sudden we started building chips with multiple cores, and pretty soon a huge number of cores, up to at least dozens. And today, dozens of cores are very common in most server chips, for example. So this trend has basically continued to the present. So we're now, your phone has 6 to 8 processor cores and about 10 billion transistors in its main chip, but it's still running at best the same 3 gigahertz or so that's been common for about 15 years. So, this presents us with a challenge. So if we want our programs to go fast on modern hardware, we need to worry not just about the sorts of stuff we've been talking about up till this point, but we also need to figure out how to use lots of cores, how to run multiple independent tasks in parallel. Okay. So with that, how should we think about what a typical multi-core machine looks like? Abstractly, it's something like this. So we have multiple processor cores. So those are each of the Ps that we have here down on the bottom. Each of those cores potentially has its own cache memory. Those are basically just like caches that we've been talking about up till this point. But to connect all these together into one large machine, we have some kind of a network. For dealing with single chip machines, this isn't just an on-chip network. It's often a lot simpler and faster than something like Ethernet or IP, but still you can effectively think of it as a network that interconnects all the processors and other all of the cores and other elements on our overall processor chip. And then we have some interface to memory and potentially I/O also hanging off of that. And the key thing about this hardware, all the kind of general purpose processor architectures that we'll be focused on, so things like x86 or the ARM cores in your cell phone, is that basically all the stuff that runs normal software like Linux and Windows and Mac OS. Key thing about those is that they provide what we call a shared memory abstraction. And what that means is that each of these independent cores, when it loads and stores values from memory, they're loading and storing from one big logically shared pool of memory. And that's different from what's often called distributed memory parallelism, which is more common in a supercomputer or a cluster of machines like in a data center, where the logical abstraction is you have many different machines, each of which have their own local memory, and if you want to move data between them, they need to send explicit messages back and forth. In standard multi-core CPUs, like the x86 processors we're focused on, we just have a simple shared memory abstraction where logically there's one big pool of memory that all the different cores can see. So all their reads and writes go to that main pool of memory. So if they want to communicate with each other, core 1 can just write a value to some address, and then core 2 could read a value from that same address and see what was produced by core 1. All right. So any questions on this so far? If you have any questions, go ahead and shout out in Slack. Oh, not too much so far. All right. So the question is, these cores still support message passing, for example, MPI. That's a good question. So at the level of the different cores interacting with each other, the underlying hardware directly and the instruction set architecture directly implements this shared memory abstraction. But there are different libraries and runtime systems that build message passing abstractions on top of that. And so MPI is one example of maybe the most widely used high performance computing message passing interface. If you write an MPI program just on a single shared memory multiprocessor, then the logical message passing can be accomplished under the covers using the shared memory. But if you want to target your MPI program to run on multiple different machines, say in a cluster, then messages between cores on the same machine can go through shared memory, but ones that are going between physically separate nodes would be routed and sent over the network. So yes, message passing programming models can still be useful on top of this, although we're mostly going to focus on, it's actually a good segue, we're mostly going to focus in this class on shared memory abstractions, so programming a single machine directly. Okay, so for the rest of today, we're going to talk a little bit about the underlying architecture of shared memory multiprocessors. So this is how the hardware provides the abstraction of a single shared memory for many different processors. And then we'll introduce 4 main concurrency platforms. So these are programming models and runtime systems with which we can write parallel programs to run on multiple processors. So we'll talk about these in increasing order of abstraction, starting from the most low-level and universal model that's really widely used, which is the raw threading abstraction provided by basically any operating system. And specifically, we'll be talking about the pthread standard, which is the most widespread version of this, although there's similar platform-specific things you'd see on Windows or Mac OS or other things too. And then we'll move up to talk about 3 different well-established higher-level parallel programming models and a bit of the differences between them. And ultimately, in this class, you'll do all your parallel programming with Silk, which is the highest level thing we're going to get to today. And today we're going to give you a little taste for why maybe you should be glad about that. But to the earlier question about MPI, you can characterize MPI as another concurrency platform, but where the 4 that we're going to focus on here deal primarily with the shared memory abstraction. MPI, again, deals with an explicit message passing abstraction. So logical MPI processes don't share memory with each other. Instead, they just have the ability to send explicit messages back and forth to each other. But that's different than most of what we're going to do. All right. So first, how do multiprocessors actually work? And specifically, how do they provide an abstraction of shared memory when in fact we have many different processors and many caches spread throughout our system? So we're just going to give a quick taste of key issues here, since basically our motivation is that understanding what the hardware has to deal with is important to understanding the potential performance pitfalls, at least some of them that can come up when using multiple cores. So the architecture of how shared memory multiprocessors are implemented is extremely rich and complicated. And if you take an advanced computer architecture class, this might be a major component of it. Some of you might have already seen this kind of topic before, but we're mostly interested in kind of the most basic issues that come up, because even as a programmer writing on top of abstractions above this, understanding the basic ideas can be important for reasoning about performance characteristics. All right, so the main thing we're going to focus on is how caches work in a shared memory multiprocessor setting. So remember, accessing main memory, so accessing the DRAM on our processor, or off our processor more to the point, is one of the most expensive things we can do on a modern machine. So to put it in relative perspective, accessing a value that's already been loaded into a register usually takes a single cycle, and accessing something from DRAM could take anywhere from like 80 cycles to potentially more than 200, depending on our machine and the condition that it's in. And that's why we have caches. So the different caches, we've often talked about having maybe 3 levels, like L1, L2, and L3. These different caches provide a trade-off between capacity for storing more data and getting more reuse out of that data, and the latency and bandwidth that we get to access values out of them. So the L1 cache might have maybe like a 3-cycle latency instead of 1 cycle for registers or 100 for memory. The L2 might be like 10 cycles, and L3 might be like 20 or 30 cycles. And if you remember from a bunch of different contexts we've seen before, caches are really critical to getting performance. If we're doing all of our reads and writes to main memory, often we're losing orders of magnitude in performance. So the caches are critical, but one of the major issues with shared memory machines is what we call cache coherence. And that's the problem of maintaining a consistent memory state visible to all the different processors simultaneously and efficiently. So let's look at the abstract diagram we have on the slide here. And suppose we have a shared memory machine with at least 3 processing cores and a local variable x storing the value 3 in memory. So if you remember, we have these different processing cores. Each of them has these green boxes, which are cache memories local to those cores. We have a network interconnecting them all and interconnecting them with memory, main memory up here, and that's the shared memory. Okay. So now imagine that, say, this first core wants to load the value of x from memory. If you think about this just like how we imagine when we're thinking about just one core, it doesn't have it currently in the cache. That value is living out in main DRAM. So we're going to have to fetch the value in from memory. Along the way, we're going to store a copy in our cache and then load it all the way into registers. So after we're done with that, our machine is in a state like this. So that first core has a copy of X in its cache. It's also stored in main memory. So now let's say processor 2 wants to load X. All right, so once again, we can just fetch it from the main memory, deposit it in our cache, and load it into our local registers. All right. So far, this is just like we would imagine with when our whole focus was a single unicore processor with a single cache hierarchy going to memory. And again, now if another processor, another core rather, wants to load X, actually a brief aside about terminology because I'm probably going to mangle this and you'll probably see it mangled in many contexts. We often wind up using processor and core somewhat interchangeably, because at the logical level, you can think of each core as a separate, the abstraction of a separate processor. It's also sometimes the case that we refer to the entire system on chip, so the entire slice of silicon in one chip, as a processor that has many cores within it. So the word processor is a little bit overloaded, whether we're talking about individual cores that run a single stream of instructions and have their own architectural state, like registers and stuff, or whether we're talking about a whole chip that might contain multiple cores. So excuse me and excuse things you may see written in the class or all over the internet and everywhere else, because sometimes those are used a little interchangeably. But the reason is basically that at the level of this abstraction, whether these cores are on a single piece of silicon or multiple separate pieces of silicon, and that whether the network is on chip or across multiple chips, to some degree doesn't matter. The basic issues are the same. And in fact, in your laptop or cell phone, all your cores are on one chip, but in the AWS machines that we do benchmarking on in this class, there's 2 main processor chips, each of which has, I think, 12 cores on it. And so this abstraction of multiple logical processors is actually spread across 2 separate chips in that setting. So just a little bit to keep in mind that the terminology can sometimes be a bit fuzzy. Okay, so now again, remember we had, we loaded a copy of X onto our first 2 cores over here, and we wound up with local copies in their respective caches. Now our last core over on the right says it also wants to load X. It wants to get in on the party. Now we can do the same thing that we did before and fetch it all the way from memory. But maybe, maybe if these are these different cores are all close together on one chip, maybe it's cheaper instead to fetch it from a different core's cache. So that's another option that we have. So we can fetch it over the on-chip network either from memory or from another core that has it in a local cache. And maybe in some cases that's faster than going all the way to DRAM. Okay, so now we have copies of X in 4 different places. We have a copy in memory, and we have a copy in the local caches of 3 different cores. But that's fine so far because they're all storing the same thing, so they all have the correct value. So if one of the processors loads X again, they can get it from their local cache. They don't have to go far away and fetch it from memory. And that's exactly what we want. Our goal with the caches is that we want most of our interaction with memory to happen to the nearby cache so that it'll be a lot faster. So at least if everybody's just reading these values, everything's good, and we basically get what we want. But what if somebody wants to modify X? Let's think about that for a second. So let's say that this core issues a store to the address of X. And say maybe we want to store the value 5. Well, if we think about how this would work normally when we just have a uniprocessor, we just update our local cache's copy. Again, the whole point of the cache is that we don't want to go all the way to DRAM all the time. That's the reason we want to have a cache here. So we just update the local copy. And from the perspective of this core, if it wants to then read it again later, it's going to see the local copy from its cache, which is what we'd expect. But remember, we have multiple cores, all supposedly seeing a single unified view of memory. So now let's think about what might happen next. So if this is the state in our system after we updated the local copy on this last core, now we have 4 different copies of X, but we have 2 different values. So now, arguably all of these values are stale. They're no longer valid. So now if processor, core 1 wants to load X, normally it would just fetch the value from its cache. That's fast, which is nice, but unfortunately it gets the wrong value. So it's still seeing X equals 3 instead of the new value that we stored of 5. Okay, so this is clearly a problem, but this is exactly what's going to happen if we just implement separate caches on each core the same as we did on a uniprocessor. The normal naive way we'd imagine caches working. And we would say that these caches are incoherent with each other, and meaning that they don't have a coherent view of shared memory state across the whole machine. And the goal of cache coherence schemes is to fix this, so we get both the illusion of a single shared memory and the critical performance benefits of caches. All right. So actually, any questions here? That's sort of what cache coherence is all about, but I want to stop if anybody has questions on what we've seen so far. Charles has a question. Or maybe he's answering just in the thread. All right. Cache coherency is hard. Ask questions, indeed. So we'll talk a little bit more about how it works, which will give a taste of where some of the complexity emerges. So that's the idea, that's the problem that cache coherence is about trying to solve. And it turns out there's lots of different schemes and they get really complex. And today we're just going to talk about the most basic scheme, but I think it still gives a good basic intuition for the core idea underlying even the fancier ones that get used in real systems. And this basic scheme we're going to talk about is called the MSI protocol. And the basic idea is this. So in addition, we have caches on each of our cores, and in addition to the tags and other metadata that are stored on each cache line, like, whether there's valid data there, how recently it's been used, maybe tag information about what global address it corresponds to. In addition to that stuff, we're also going to store some extra metadata that labels that cache line with a cache coherence state. And for this MSI protocol, you can see where the name comes from. There are 3 possible states for each cache line. They're creatively called M, S, and I. And what they mean is, if a line is labeled M, that cache line has been modified locally in that cache, and no other caches are allowed to contain that block in either the M or the S states. I'm using block and line interchangeably here, so apologies for that too. The S state means that other caches may also have copies in the same S state. So S corresponds to lines that are shared and potentially replicated among multiple caches at once. And then the I, or invalid state, means that cache line has been invalidated. It's the same as it not being there. If we try to look up that value in the cache, we won't get a hit. And so we won't consider that data to be there. So then the key rule in the protocol is that anytime a core wants to write to a cache line, remember that was the key moment we had an issue. Anytime we want to write to a cache line, we have to be sure that we've first invalidated every other copy. All right, and we can see a little bit about how that works. So let's say we have 4 cores with 4 separate caches storing the data in the states that we see here. So, core 1 has the value 13 for the variable x, and it's in the modified state. Notice no other core has a copy of x except ones that are invalidated, so they basically aren't there. Core 1 has the variable y with the value 17. It's in the shared state, and we can indeed see there are shared copies also in 2 of the other cores. Those are all coherent. They store the same value. And then for the variable z, we can see that core 2 has it in the modified state, and there are invalidated copies that have been, there are stale copies that have been thrown away in 2 of the other cores. Okay, so that's where we're starting out. And now what happens if, say, this core, the second core, wants to store the value 5 to the variable y? Well, if we look at our local cache, we see that the line for y is in the shared state. And that means that some other cores caches may also have copies of it. And so to avoid incoherence, to avoid problems here, before we write to it, in the MSI protocol, we first have to send a message to all the other cores to invalidate their copies of y. So this core or this cache is going to say broadcast a message to everybody else that might have a copy saying, you need to invalidate this cache line, your copies of this cache line. So now we can see those other caches have invalidated their copies of that line. And so this core is the only one with a valid copy of y. So notably, if these other cores went to read y, they could no longer get it from their local cache. They're no longer allowed to read this. It's effectively been evicted. Okay, so now finally, we're in the state where we're ready to write a modified value to our local cache here. So once we do that, we update our local cache with the new value for y. So we put 5 in y. And we also change that cache line to the modified state. And when it's in that state, the system knows that this is the one true up-to-date value for y. So right now, we have one true local value for x, one true value for y, and one true value for z. And if we want to fetch any of those values from any of the other caches, they don't have them. They've been effectively evicted. This question comes through, why can't we broadcast the new value directly to other caches? We're going to have to send a message to invalidate them all anyways. That's a great question. And the issue here, in fact, is not on the first update. I'll talk about this more in a second. The issue is that in general, it's very expensive if all these cores are modifying the same values at the same time, because they're going to be constantly having to communicate with each other to update values. If everybody's fighting a war trying to write new values over all the same, say all these same 3 variables really fast at the same time, then we're going to be broadcasting messages all over the place, invalidating and fetching updated copies, every few cycles potentially, and that would be really slow. But the observation behind this scheme and other schemes is that ideally, most of the time, a given variable or a given line in memory is only being used, over a short time period, is only being used by one core. And so by allowing things to be in a modified state, instead of constantly broadcasting updates everywhere, we allow, say, this core to locally update the values for y and z repeatedly without having to communicate globally. So once we've done that one broadcast to invalidate these things in everybody else's caches, as long as nobody else touches those for a while, we can locally do a whole bunch of work on them just as efficiently as if we were the only processor in the world. And so that's really one of the most fundamental issues here. So each time we want to load a value, we have to check whether it's in the M or the S state. If it is, we can load it locally. Each time we want to write it, we have to check if it's an M. If it is, we can just mutate it locally. If we don't have it in the M or S state and we want to load it, we have to fetch that line from another cache in the system or from main memory. And if we want to modify a value, as we saw, we need to make sure to invalidate it and claim a local modified. Basically, this modified state is like an exclusive ownership bit for that piece of memory. So if we want to modify things, we need to make sure that we have ownership over them first. All right. So that's the basic idea of MSI. A few other observations. So first, when we write values to our caches, we actually have some choices. So we can either have what are called write-through caches, where when we write a value, we also keep writing it all the way up the memory hierarchy, all the way, further back, potentially all the way to main memory. Or more commonly today, most caches are what are called write back, where we only update a given level of the cache, and then only when someone else needs the value do we actually spread it further. Another observation, we've been talking about this at the level of variables, but for efficiency reasons, tracking this extra metadata, communicating every time anything gets, potentially changes state, moving values around is expensive. And so we need to amortize it. And so for a whole bunch of efficiency reasons, this is generally done at the level of cache lines, not individual values. So again, that might be like 64 bytes in the x86 or ARM processors you most commonly see today. And reasoning about that can be important for doing back of the envelope calculations about how often you might be invalidating lines in different caches, depending on how close together values are that different cores might be trying to read or write at the same time. It turns out that this MSI protocol, like I alluded to at the beginning, is really a very, very simple one. It only has these 3 states. You can make it more efficient in practice by adding additional states. You might more commonly in real life see MOESI, where the M, the S, and the I all stand for the same thing, but you also have unmodified ownership states or exclusive access states or other things like that. But the basic idea is the same. The state machine gets more complicated. The number of types of messages you have to send gets more complicated. But broadly, the flavor of how cache coherence works is pretty similar to this. But as Charles emphasized, the actual implementation of these protocols is monstrously complicated and has been one of the biggest sources of bugs in actual shipping hardware in the last few decades. And it turns out this is actually also one of the first cases where formal verification for verifying correctness of real commercial systems came into widespread use. So, most cache coherence protocols in real systems you interact with today have probably been formally verified, because otherwise it was just too hard to make them work at all. Okay, so with that, before I move on, any other questions on this stuff? Seems like most of the little questions that have come up have been getting answered in discussion, which is great. So that was just a quick taste of the architecture of shared memory multiprocessors, which is how basically all the standard multi-cores we use today work. So now I want to look just a bit at how we can actually program these things. And again, we're going to focus on 4 different common concurrency platforms. So first, what do we mean by concurrency platform, and why do we need one? So a concurrency platform, well, first of all, it turns out, and you may have heard, that parallel programming and concurrent programming, programming multi-core machines to do multiple things at once, is really painful and error prone. And in particular, doing it at the level of the actual instruction set abstraction, so at the actual level of the semantics of x86, for example, and its memory model, which is relatively weak, is ridiculously hard. Much more useful are different common abstractions that sit on top of the underlying primitives that the hardware provides. and abstract things like processor cores, how synchronization works, how we communicate between different cores, and potentially also things like how we multiplex or virtualize our hardware, like how we load balance when we have a different number of tasks, potentially many more tasks than we have physical cores at a given point in time. And that's the role of what we're calling concurrency platforms. And the four key examples that we're going to talk about here are the basic standard low-level threading APIs. So this includes things like pthreads, as well as, like I said, platform-specific variants of this that you'd see on Windows or other things. And also persistent thread abstractions that you might have on the Java virtual machine. So this is the first and most basic form of parallelism and concurrency management available in Java also. They all look roughly like pthreads. Pthreads is just a nice standard. Then we're going to look at three slightly more or progressively more abstracted concurrency mechanisms: threading building blocks, OpenMP, and Silk. And we're going to focus in particular on Silk because both because it's a tool developed here at MIT and because it's really nice, and because of both of those things, it's what we're going to be using for all of the parallel and concurrent programming we do in the rest of this class. So right now we're going to talk about three other models, but everything that you're actually going to do in your own homeworks and projects, I believe, is going to be in Silk. All right. Now, to look at how different concurrency platforms let us write parallel programs, we're going to focus on a really simple problem, which is trivial to parallelize. And that problem is computing Fibonacci numbers. So you might remember Fibonacci numbers are the sequence, comes up in different math classes or fun puzzles a lot. They're the sequence 0, 1, 1, 2, 3, 5, 8, 13, etc., where each number is the sum of the previous two numbers. So formally, we can define them as this simple recurrence. So Fibonacci number 0 is 0, Fibonacci number 1 is 1, and then for any n above 1, Fibonacci number n is equal to the sum of Fibonacci number n minus 1 and Fibonacci number n minus 2. Fun history, they're called Fibonacci numbers. They're named after a nickname of Leonardo da Pisa, who wrote a book in which did one of the first widely recognized studies of this sequence in the West around the year 1200. The name Fibonacci is actually a contraction of Filius Bonacci, meaning son of Bonaccio. I guess that was his father's name. So Fibonacci was responsible for introducing the study of the sequence in Western mathematics, but it actually turns out it had been studied for at least centuries before that by Indian mathematicians. All right, and so that's what we want to compute. It's going to give us the basic skeleton of the algorithm that we want to try to parallelize. And the algorithm that we're going to use to compute Fibonacci numbers is just a direct translation of that recurrence formula. So in C, it's going to look like this. So we just have a function fib of some Fibonacci number index n. And we have our base case for n less than 2. Fibonacci 0 is 0, Fibonacci 1 is 1. And otherwise, we're in the recurrence. We just basically transcribe the recurrence relation. So the ultimate result is the sum for Fibonacci number n is the sum of Fibonacci n minus 1 and Fibonacci n minus 2. We're just implementing that recurrence directly as a recursive algorithm. And then we have some cruft in C to actually take as an argument which Fibonacci number we want to compute and then print the result out. That's all that's going on. All right, does that make sense? So at some level, it shouldn't make sense. I mean, it's a nice direct transcription of the recurrence, but a quick disclaimer, this is actually a really terrible algorithm. You could pretty easily come up with a simple linear time algorithm by computing all these values bottom up. It turns out there's an even better, if you want to get clever, there's a logarithmic time algorithm based on squaring of matrices. But if you look at what we're doing here, when we compute fib of n minus 1, that's also going to compute fib of n minus 2, but we're computing fib of n minus 2 here. We're computing a whole giant tree of values redundantly. So this is, I think, exponentially worse than it has to be. But we just, in this case, we don't care. We're just taking as a given that this is the algorithm an app developer gave us and wants to use. And our goal is to make it faster. You know, we're performance engineers. Our goal is to make it faster by running in parallel on multiple cores. I mean, general side comment, it is always useful to make sure you're using an efficient algorithm before you get down to other aspects of performance engineering. But in this case, this is a nice kind of simple skeleton structure for thinking about parallel execution. All right, so this is the core recursive computation that we're going to get. This is the core recursive function, and this is the tree of invocations that it'll expand into for example, the fourth Fibonacci number. So at each node in the tree, we're computing the two predecessor Fibonacci numbers and adding them together. And the key idea for parallelizing this is to observe that each time we branch, the two branches are independent. So for fib n, say fib 4 here, fib n minus 1 and fib n minus 2 can be computed totally independently. So these two subtrees are completely independent. They don't interfere with each other, and they can be run in parallel. So that's a basic idea of what we want to do with our parallel program. All right. Now I want to take a quick 2-minute stretch and breather break, and then we'll dive into how we start parallelizing this with different tools and frameworks. That's fresh tea. Okay, so that recursive Fibonacci, we're parallelizing the different branches of the tree. This is the basic thing that we want to try to implement. So now let's look at some of the different frameworks we can use to implement that parallel Fibonacci algorithm. And we're going to start out at the lowest level of abstraction here with pthreads. So pthreads is a standard API for writing parallel code using what's often called a threading abstraction. And it's an actual ANSI and IEEE standard. It's part of the POSIX operating system interface standard. So it's implemented on basically every widespread operating system you use today, like Linux and Windows and Mac OS and iOS and so on. And you can think of pthreads so it's implemented on all of those things. And like I've been alluding to before, there's also kind of equivalent, very similar models in the Java virtual machine, in the raw Windows API, on top of which their POSIX interface is implemented, or in the low-level kernel APIs on Linux and Mac OS too. But you can think of pthreads basically as kind of a do-it-yourself concurrency platform. And in fact, it's usually the abstraction on top of which all of the other abstractions we'll see are built. And pthreads, evolved as the threading interface of the Unix standard, basically. It's implemented as a library of functions exported in C. But critically, those functions interact with the operating system and do clever low-level hacks at the level of machine assembly internally. So they don't have strict, simple C function call and return semantics. And instead, we can use them together to launch multiple threads, where each thread logically is like a separate copy of our program with an abstraction of its own processor on which it's running. And then potentially many threads are multiplexed onto the physical resources, the physical cores of our machine over time. And in pthreads, like in all of these things, we have a shared memory abstraction. So the threads communicate by reading and writing values in memory. And synchronization primitives also work by using special instructions to interact with memory. And then pthreads has a bunch of library functions that mask the low-level protocols involved in actually communicating between processors on the underlying hardware. All right, so the key functions that we care about in pthreads, the two most basic things, are pthread create, which launches a new thread, creates a new thread. The arguments to that we've documented here are relatively self-explanatory. So this is kind of ugly low-level Unix EC. So the return value is actually passed as an argument, a pointer to where we want the return value to go. So this first argument is where pthread create is going to return the identifier struct for the thread that we just created. The second argument is a set of thread attributes, which can control various aspects of how the thread's going to work. For our purposes, doing really simple parallel programming, this is just null. We get all the default configuration. And then the key parts are a function pointer, which is the routine that this thread's actually going to run. So it's sort of the main entry point, but for what this thread's going to execute. And then a single void star pointer to the argument that should be passed to that routine. So, we're creating a new thread, we're spawning and running a new parallel thread. What code should that run? Well, it's going to run the code in this function. So it's basically like a callback. We're saying, please create a thread, and when you've created it, it should jump to and start executing the code in this function and pass it this argument. And then the other main thing we have to, the most basic way we can synchronize with those threads is with the pthread join command. So pthread join takes one of these thread IDs and waits until that thread has finished, has returned, basically. So this lets us spawn off a thread and then wait for it to complete. Now, if we want to use that to parallelize our Fibonacci code, we get something like this. So this was just our original simple, recursive Fibonacci routine. We're also introducing a new data structure for passing the arguments, because remember, we have to pass them in a single void star pointer, so we need to pack both the input and output values from that function into a struct. That's the struct we're going to use to do it. This is the function that's going to get called when our thread is created. We're calling it thread func. Again, it's a void star function taking a void star argument. What it's going to do internally is just unpack the input from the argument pointer, pass that to fib, capture the output of fib into the output of the void star data structure, and then return because it's done. Okay, then over here we have the main code. It's gotten a little bit more complicated because we have pthread setup stuff. We're still, checking and grabbing the n that people want to the Fibonacci number we want to compute from the argv args. Because we have a little optimization here. We're saying we're not going to bother parallelizing if n is less than 30 because there's not enough work to do. It's only if n is 30 or greater is it fruitful to parallelize in this way. That was just determined empirically. So in this special case, we're just going to call fib of n like we normally would have. We're not using multiple threads at all. But otherwise, if n is big enough, we're going to marshal the input argument to the threads. We're going to take the n minus 1 that we want to run and pack it into an arg struct. We're going to actually create the thread to run that. So we're going to create a thread that's going to run this thread func, and it's going to pass in a pointer to this arg struct in which we stuck the input. Then we ourselves in the main thread are going to run the other recursive call, fib of n minus 2. But remember, this one was running off in parallel with us. So then when we want to actually complete, we need both of those threads to have finished. So we join on the thread that we forked. And then add its result, which is marshaled through the arg struct into our result, and that's the ultimate Fibonacci result. All right, any questions on this so far? Again, you're not really going to be responsible for writing lots of low-level pthreads code. This is kind of the most simple example you could make. It's kind of ugly, but it gives you a little bit of a sense of what it would entail. And one observation about this is, so how many cores are we using here? Does anybody have thoughts? So we potentially have like 24 cores in our machine. Is this going to do a good job using all of them? Yeah. A bunch of people have noted we're only using 2 cores. We only forked 1 thread here, and then we still have the main thread that started up when our program started. So we're using 2 threads to do all the work. So that's not great. We could do more, but we would have to write significantly more complicated code to do it. So that was already kind of messy and complicated, and it's worth pointing out some of the general issues with pthreads. So the first is overhead. So it turns out that the cost of creating a new thread is actually pretty high, like tens of thousands of cycles. And that means that we can't just treat, that was the reason that it wasn't fruitful to even fork with second thread if n was less than 30, even though we're using a doubly exponential algorithm. We need to be doing a lot of work for it to be worth spawning threads. And that basically means that we need to be carefully structuring our program so that we're working with concurrency at a fairly coarse granularity. And we can reduce some of the constant factor overhead here by using the idea of thread pools, which is that at the start of our program, we can spawn a whole bunch of threads. And what each of those threads actually does is sit there waiting for work to be fed to it, potentially on some kind of work queue or something like that. Then when we want to actually launch a parallel task, we don't have to literally start a new thread. We can just grab one of the threads out of the thread pool and feed it some work to do. That can help with the overhead. It makes, at the pthreads level, it makes the code significantly more complicated. And that's actually a big part of what the higher level concurrency platforms are going to do for us. But even so, we need to worry about the granularity and overhead of working with multiple threads. The second observation here is that this code got pretty ugly, but even with that, the speed up isn't very good. So we noted that we're only using 2 threads. That's part of why, only using 2 threads and therefore using at most 2 cores. So that's part of why. But the speed up on an actual machine last time we measured this was only about 1.5, which is still, it's only 50% speed up using 2 cores. Does anybody have any ideas for why that might be? Why aren't we getting closer to 2x? Yeah, so the intuition is the runtime is going to be the slowest thread. And the observation here is that the recursive tree of Fibonacci calls we have is imbalanced. So the fib n-1 and fib n-2 branches are actually different, it turns out, by the golden ratio, or about 1.6 in terms of how many nodes are underneath them. And so that basically explains the factor here, that the difference between the 2 branches is imbalanced by about 50%. So one of the threads is going to be idle significantly more than the other one. We're waiting for the other one to complete. Now, this will get way more complex still if we wanted to parallelize better to get better load balance, use more than 2 cores. And remember, even your phone has 6 to 8 cores today. So, this is just barely scratching the surface. Maybe worse, the Fibonacci logic, even in the simple version, is no longer neatly encapsulated inside the fib function. If we look back at the code, we actually have the recurrence written out here. We also have some variant of some kind of base case here, and we're adding together values here, which is equivalent to this. So like we've replicated the basic recurrence and add, recurse twice and add together structure several different places in our code. So we're losing modularity, and even just at the most basic level, the code is arguably a total mess. The level of abstraction of this API, reminds us of time when even Professor Lyserson was much too young to code. We don't have normal function calls. We're manually marshaling the arguments we want to pass to this thread through a weird data structure, passing it with void star arguments. And, this is all like, we have to have a calling convention where we're explicitly sticking values in memory to pass arguments to functions. That is basically like programming an assembly on the first computers. This illusion in 1957 is because 1957 is when I think Fortran 2 came out. Maybe it was when the release of this is the release of the first version of Fortran, which is the first high-level programming language developed at IBM in the mid-50s, which is the first thing that let you program much above the level of assembly and have an optimizing compiler and all of that. But it turned out that first version of Fortran didn't yet introduce the idea of subroutines or function calls. And so you could write expressions of multiple terms. You could write loops and other math, but you couldn't have subroutine abstraction. And so you still needed to do that almost at the level of assembly. And it was only in Fortran 2, a little bit later, that they introduced subroutines, which are basically something we totally take for granted today. Fun fact, in addition to this being before Charles was in elementary school, this is also right after my dad was born. My dad's first job, about 13 years after this, 12 years after this, was at the same IBM research lab that developed Fortran. All right, enough of the history. Basic idea, we don't want to be programming like it's 1957, because that was a very long time ago and we've got better ways of doing things. Okay, so with that, let's move up the stack and look at some higher level abstractions that we can use. So the first common one that you'll see used somewhat widely, you may well encounter in jobs in industry. It's a pretty useful toolkit. It balances convenient abstractions while still giving lots of control and high performance, is threading building blocks, which was developed originally by Intel and open sourced maybe 15 years ago, something like that. So threading building blocks is a C++ library. It's written, again, at a somewhat higher level of abstraction than the native threading libraries like pthreads, but it runs on top of the native threading abstraction. So on most machines, you'd see it running on top of pthreads or raw Windows threads. And in general, threading building blocks raises the level of abstraction from threads, which are basically just independent processors, logical processors running separate programs in a sense, to what we call tasks, which are more like, a little bit closer to function call and return. And those tasks, instead of owning a logical core indefinitely, run for a finite amount of time and are logically load balanced across multiple physical threads running on our physical cores using a work stealing algorithm. And that work stealing algorithm is actually underneath all three of these higher level abstractions we're going to talk quickly about, and was inspired by research from about 25 years ago here at MIT, mostly in Professor Lyserson's group. All right, so really quickly, a small taste of what this same function might look like in threading building blocks. We'd write some C++ code like this. So the main Fibonacci logic's on the left, and again, our main is set up on the right. In TBB, computations all organized into explicit tasks. Tasks are defined as classes that inherit from this generic task class. And so the arguments are passed, are passed in by initializing members on that class from its constructor. So a fib task has an input parameter n and an output parameter sum. And then every task has to define an execute function, which is the actual callback logic that's going to perform when the task is started. So in this case, execute basically looks just like our old recursive fib, with just a little extra detail to spawn some parallel children. So if n's less than 2, the result is just n. Otherwise, we recursively create two child tasks, A and B, for fib n-1 and fib n-2. Then we do some weird TBB specific stuff, set ref count 3. Turns out that's setting the reference count of the number of tasks we're waiting on to 3, which is the number of children here, which is 2, plus 1 extra one that they always make you keep around for bookkeeping. Don't ask me why. Seems like they might have had, dealt with that automatically, but that was the abstraction they came up with. Then we spawn the task B, and then we spawn and wait for all the child tasks, spawn A and wait for all the child tasks. In other words, wait for both A and B to finish. And then by the time we pass that line, we know both A and B have finished. And so we have the X and Y results back. And we add them together and return those as our own result. Then in the main task, we basically, do some similar TBB magic so that we kick off the base thing as a root task and wait for it to complete. All right, any questions on this really quickly? Again, this is just a taste of tools you may see in the wild, but not something we're going to ask you to write code in. Oh, it doesn't matter that we spawn B before A. No, related to these being independent, they're also associative and commutative. We can run these tasks in any order and we get the same result. The two subtrees are totally independent of each other. We could spawn B before A or A before B. Okay, so TBB has a number of other features and higher level abstractions built on this basic task abstraction. So it has rich template library for common higher level parallel patterns like parallel for simple parallel loops, parallel reduces, where you want to, like in a MapReduce kind of setting, you want to do summation or data aggregation. Also has pipeline and filter constructs for building parallel DAGs of independent tasks. It provides concurrent container classes that allow multiple threads to safely interact with things like, maps and queues and vectors in a safe concurrent fashion. And it also provides lower level mutual exclusion and synchronization primitives for things like locks and atomic updates. So TBB is a nice library if you want to program at a relatively low level, but want to eliminate some of the nastiness at the pthreads level. Next, we're going to talk really quickly about OpenMP. So OpenMP is another, like pthreads is another industry standard. It's actually a continuously evolving one still today, specified by an industry consortium. I don't remember what standards agency owns it, but it's a language extension to C. So where the others that we've seen so far have been implemented effectively as libraries in C or C++, OpenMP is a language extension that has to have it, requires explicit support from your C compiler to implement it. And there's a fair number, fairly widespread support for at least parts of it today. So GCC, the Intel C compiler, Clang, which we're working with, and the Microsoft's Visual C compiler all have support for some version of the OpenMP standard today. And the basic idea of OpenMP is that it provides some simple language extensions. We'll see them in C and C++. They also have variants that appear in Fortran, which is still used by high-performance programmers, high-performance computing programmers today. And those language extensions basically all come in the form of what are called compiler pragmas. I'll show you what those look like concretely in just a second. But these are basically extra directives that let you annotate a statement or a line of code in your C code, telling the compiler something about how that statement should be interpreted or executed. And the basic idea when OpenMP started out was that these pragmas are entirely optional. And so your program should have the same meaning whether those pragmas are applied and things run in parallel or not. Turns out more recent versions of OpenMP have added a bunch of features that aren't robust to being ignored. You can make programs that are only valid if those pragmas are implemented properly, and not if they're ignored. But that was kind of the basic idea. Again, like everything else, it runs on top of native threads. So it'll run on top of your OS threads or pthreads library. And it supports kind of standard abstractions for loop parallelism, so parallel for loop, task parallelism, like we saw with TBB, as well as pipeline parallelism. So if we want to do our simple recursive parallel Fibonacci in OpenMP, it looks something like this. So this is actually the first thing that's really starting to look arguably pretty nice. So this is just exactly the same as the recursive code we started out with in our original starting program. But where we have the two recursive calls, we add these OpenMP pragmas. So pragma OpenMP task shared xn is an annotation that applies to this statement, x equals fib of n minus 1. See a similar pragma on y equals fib of n minus 2. And then we see this pragma OMP task weight. So each of these pragmas, again, is a directive to the compiler. What they mean successively is pragma OMP says we're making OpenMP directives, so that they should be interpreted as such. The task command means that the following statement is an independent task. So this function call, instead of blocking until it returns, could be run on a separate thread, run as a separate task. And then this shared directive says that, so this task isn't just the call to fib, it's the call to fib and then the assignment of that to the variable x. So here we're saying that the variables n and x, we have to do some kind of synchronization to make sure that we're reasoning about that these are safe to share between the parent thread and the child threads, because we're sharing those stack variable values in memory between the different threads. And then at the end, task weight is like the pthreads join or the weights in the TBB version, saying before we pass this point, we have to wait for any tasks we've previously spawned inside this function to complete. And then we just add the results together and return, same as before. All right, so OpenMP provides lots of pragma directives like this, again, to express different common patterns, somewhat similar to things you'd see in TDB, such as parallel for loops, which are maybe the most useful and most widely, the things you'll most often see OpenMP annotations for. So you can annotate a for loop with pragma OMP parallel for, and that for loop will run in parallel. It also supports annotations for reduction and for controlling scheduling of the parallelism and data sharing between different threads and so on for different tasks. And then it provides its own set of synchronization constructs, such as atomic updates and locks, and also slightly higher level constructs that are useful for things like parallel tasks and for loops like barriers. Okay, so with that, I want to quickly dive into Silk before we wrap up. So Silk is the highest level of the abstractions we're going to talk about. And it's got long roots here at MIT and specifically in Professor Leiserson's group. So it's been around for, it's been in development for, I think, more than 25 years in different forms in different places, but originally starting here and most recently again here. It's won lots of awards and had lots of impact on how people think about parallel programming and parallel algorithms. But Silk itself is kind of like OpenMP, a simple linguistic extension to C and C++ that supports a task-based parallel programming model. But the nature of that linguistic extension is a little bit different. So it adds new keywords directly to the C language, specifically designed for supporting a fork join model of task parallelism, which we'll talk more about over the next few lectures, I think. And importantly, underneath Silk and underneath also these other high-level abstractions like TBB and OpenMP, which inherited this idea from Silk, is a really intelligent scheduling algorithm based on an idea called work stealing. I think later on we'll talk about how that works. But the high order bit is that for the class of parallelism expressible by Silk, a work stealing scheduler is provably efficient in a bunch of useful ways. Like it's asymptotically as good as you can do on a bunch of different axes. It also provides some additional constructs like a reducer library that we'll introduce for parallelizing code that interacts with global variables, interacts with shared variables across tasks. And it has a really useful ecosystem of tools that we'll use in this class, including a race detector and a scalability analyzer that help debug parallel bugs and do performance tuning and performance profiling of parallel code. In 6172, we're specifically going to be using the latest and greatest Silk implementation, which is called OpenSilk. we're using, I think it's getting very close to a full public release. We're still using one of the latest betas of the compiler. So OpenSilk is based on a project that started, I don't know, 6 years ago, something like that, here at MIT by T.B. Shartle, who has taught previous iterations of this class, Billy Moses, who's currently a PhD student here, and Professor Leisterson. Its compiler is generally better than, it's the big push in OpenSilk has been advancing the state of the art in what kind of compiler optimizations can apply to parallel code by pulling notions of parallelism into the LLVM IR. So OpenSilk does a better job letting the compiler optimize parallel code than almost all these other frameworks where the parallel constructs are totally opaque to the compiler. And we'll learn more about the OpenSilk runtime system in, I think, a week and a half. We'll hear from actually the developer of the core runtime system that OpenSilk uses, Angelina Lee, will be giving a guest lecture. And then again, the tools ecosystem includes race detector and scalability analyzer that we'll get to use in our projects. Okay, so this is what recursive parallel Fibonacci looks like in Silk. So this is probably the very closest we got to a kind of minimal modification of our original recursive Fibonacci function. So again, we just have simple Fibonacci, and then we have the two recursive calls, and then we introduce just these two new keywords, silk spawn and silk sync. And what these mean is silk spawn says that that's an annotation we put before a function call, and it says that that child function can execute in parallel with the parent caller. So instead of handing control directly to the function and waiting for it to return like a normal C function call, we can execute it in parallel. And then silk sync means that the control can't pass that point until all the children that we spawned have returned. So it's a barrier at which, you know, we have to wait for the child to have completed before we can proceed. And by that point, you know, we've received the X value, so we can compute the final result. A key thing about Silk is that the Silk keywords don't actually dictate how the program is parallelized. Instead, they just expose opportunities for parallelism. So Silk is carefully designed so that programs are safe to execute sequentially or in parallel, with potentially many different parallel execution orders, subject to the basic semantics of spawn and sync. So you can just ignore these spawn and sync keywords, and the meaning of the program should be the same. There's also some useful additional keywords that build on top of this in Silk, like Silk for you'll probably wind up using a lot, which is basically just a simple parallel for loop. We saw versions of this referenced in a couple previous lectures. This just says that this for loop should be run in parallel. Under the covers, this is actually internally transformed basically into silk spawns and silk syncs, which are the underlying primitives the language actually has. Again, like I was saying, Silk is carefully designed so that what we call the serial projection of the Silk program, which is basically when we just elide or ignore all the Silk keywords and get a simple serial program without them, that's always a legal interpretation of the program's semantics. So these keywords, again, give the system opportunities to potentially execute things in parallel, but they don't require it. And one trivial way we can get this serial projection is just by pound defining all these keywords to be basically no-ops. So, okay, so the parallelism is only enabled by the Silk runtime. It's not explicitly controlled, you know, more like with pthreads or something like that. So how do we actually get this stuff scheduled and run in parallel? Well, it turns out that the Silk, you know, at the core of Silk, in addition to these language and compiler extensions, is a runtime system that maps the executing program onto the processor cores dynamically at runtime. And it uses a work stealing algorithm that we'll learn more about to figure out kind of when and how to fork off and distribute parallel tasks, and where those should be migrated in the machine, which processors should run which tasks when. At a really high level, you can think of the compiler pipeline looking something like this. So we have the source of a Silk program. We feed it through a Silk compiler, which is basically an extended C compiler, and we get a binary that we can run on our multi-core machine, and we get good parallel performance. Leaving out lots of details, but Similarly, I mentioned that you can also, one of the nice things about Silk is that since it's been designed so that the serial projection is semantically equivalent, if you're using all the constructs correctly, you can do all your normal testing like you would on a regular serial program. So you can take the serial projection of your Silk source, run that through a regular serial C compiler, and run regular serial regression tests, and get reliable, reproducible, single-threaded code that's really easy to test, to step through with a single-stepping debugger and all that kind of stuff. And you can chase down basic algorithm bugs much more easily like this than you can with code that fundamentally has to be run in parallel in order to run at all. Because when you're running things in parallel, you often have different kinds of determinacy bugs, where the order in which you execute things might determine whether the bug appears or doesn't, or how it appears. I think the Silk compiler itself also has a mode that lets you compile it in serial mode, so you don't have to literally elide the directives. And again, the promise is that the parallel program executing on one core should behave exactly the same as the execution of the serial projection. C semantics, let you shoot yourself in the foot in a few ways. So there's also infrastructure that we'll see to compile and simulate the execution in parallel and identify potential race bugs. And the design of Silk and the Silk compiler makes it so that any potential bugs you might have that would make your program not safe to run in parallel can be localized and identified by this tool chain, which is a million times easier than trying to debug pthreads code. And when reasoning about the parallel performance, there's another mode that sort of compiles with some profiling information enabled and can tell us about how well your program will scale onto larger machines. Okay, so that's sort of a whirlwind tour of different parallel programming systems and of Silk in particular, which we're going to be using in the next project in this class. So just to wrap up, processors today have lots of cores on them, and obtaining high performance because of that fundamentally requires writing parallel programs. Programming directly on processor cores or even on relatively lower level concurrency abstractions can be really painful and error prone. But fortunately for us, people have developed better higher level abstractions, and the one that we're going to focus on, Silk, abstracts multiple processor cores, how synchronization and communication are handled, and performs provably efficient load balancing of our tasks on the underlying hardware. So using that, in the next couple lectures, we'll learn about determinacy races, parallel algorithm design, and other things, and how the Silk runtime system is built. In the next project, which comes out, I think, on Thursday, we'll be using this to build Screensaver and accelerating that as a parallel algorithm using these Silk tools. So thanks. And with that, I'll hang around for a few minutes to chat with anybody who wants and answer any questions. A couple of people ask, are there performance benchmarks for the TBB versus OpenMP versus Silk implementations of the FIB program? I think that's been done at various points. My apologies that it's not up to date in these slides, but we could potentially get that to you offline. I don't remember whether this appears in any of the homeworks. I don't know whether I unfortunately haven't worked through all the homeworks yet myself. But roughly speaking, I think our OpenMP, Silk, and TBB versions are probably all in roughly the same ballpark. Because those are all pretty high quality, those are all very similar implementations to each other, both in terms of how we decompose the program and in terms of how the underlying scheduler is going to work. And they're all high quality runtime systems. The pthreads version is fundamentally slow because we didn't recursively parallelize, we only parallelized once. All right.